So good morning or good afternoon, ladies and gentlemen. It's my pleasure to have Professor Mohsen Rahmani today. He's from the Nottingham Trent University, and he's going to talk about the very important question, metallic or dielectric metasurfaces. Which one is better? Can you go ahead, Professor?
Okay, thank you so much. Thanks a lot. So can you hear me? I'm not muted, no?
Yes.
No, okay, perfect. Thank you so much for the invitation. So I am Mohsen Rahmani. I am a Royal Society Wolfson Fellow and UKR Research and Innovation Future Leaders Fellow. And through these fellowships, I have come back to the UK to create the Advanced Optics and Photonics Lab at Nottingham Trent University, Department of Engineering. And it's my great pleasure to give this talk. As it was mentioned, today I'm going to speak about this metallic or dielectric metasurfaces, which one is better. So it is a very important question, and it has been a subject of debate maybe in the last decade, 10 years, and it is still a subject of debate. So I want to tell you that, there is not really black and white answer to this question. And during this talk, I'm going to share with you my own experience and my own understanding and my own conclusion on this, because metasurfaces are really wide and they have a lot of application in different directions. So I'm mostly going to speak about the application which I have been involved, and I have been doing my research mostly on that. So it's a part of actually kind of metasurface where I do that. I do my research, and in order to show you that how difficult it is to answer this question, I have put these two photos. This one photo is just right before my PhD in the left-hand side. It's before I start doing my research, which was mostly on this question, and now some years after that, and you can see that it had a little bit effect on my appearance to my effort to answer this question. So I wish answering this question was much easier, but it is not. As mentioned, I'm from Nottingham Trent University, and obviously it is in Nottinghamshire. The luxury we have in Nottinghamshire that we are right in the middle of England. That's why we can drive to 85% of the cities of the England by less than 1.5 hour driving. It is actually a big luxury, to be honest, because I'm coming from Australia. Before UK, I was in Australia, and it would be dream in Australia to reach other cities in 1.5 hours, because Australia is huge. But this gives us a good chance for networking. So therefore, we can really travel physically to the other cities much easier post-COVID, of course. And we are very open, and we are very happy to host all other colleagues from England, from the UK and Europe, and anywhere from the world to come and visit us. So if you are interested in any kind of collaboration, we are very open, and we will be very happy to do collaboration on the research direction, which I'm going to speak about today in this talk. So if still Nottingham doesn't ring any bell to you, I just want to remind you that Nottingham is the city of Robin Hood. So I hope now you can make some connections to this nice city, and next time you come to the UK, please consider visiting us. You are very welcome here. So I start my talk with saying that what are metasurfaces? Metasurfaces are actually structured surfaces where the dimension and the separation of those structures are smaller than the wavelengths of the light. So this is not the only way that light interacts with matter. We have some other light-matter interactions, like matter interaction with gratings, when the dimension and separation of nanostructures are on the order of the wavelengths, or maybe geometrical optics like lenses, where the dimension of those objects are much longer than the wavelengths, or we even have the homogeneous surfaces. So metasurfaces are actually indeed a part of light matter interaction, and they are not the entire light matter interaction. Today, we are mostly speaking about the metasurfaces. And as you saw in my title. So we are going to mostly speak about the metallic and dielectric metasurfaces, advantage and disadvantage of each of them, and the application of them in which I have been involved. In this talk, I'm mostly going to speak about the application of the metasurfaces because it gives us a better sense to understand that how useful those devices are and how we can use this research in our daily life. So I start with metallic metasurfaces, which are obviously based on the exciting the free electrons on the surface of the nanostructures excited by electric field of light and so-called surface plasmons. And the surface plasmons can be designed to be resonant at certain wavelengths and certain frequencies, so-called surface plasmon LSPR, localized surface plasmon resonances. But the matter is that the Plasmonics and this LSPR are mainly electric resonances. And of course, with some efforts and making some split rings or some complicated structures, we can also induce some magnetic fields and then magnetic resonances via plasmonics nanostructures. But it is not the general case, magnetic resonances. The general case is electric resonances of which can be induced by metallic nanoparticles. So in order to categorize my talk in a better way, so I have categorized these metasurfaces to linear and nonlinear regime. And shortly I speak that what is the difference between them. And each of these metallic or dielectric particles or metasurfaces can be studied in linear or nonlinear regime. When we are speaking about the linear regime, indeed we are in this area where the response of the material, the response of the light after passing through the material or getting reflected from the material actually depends linearly upon the intensity of the incident light. So in other words, the wavelengths of the light doesn't change, and we are working on manipulating mostly the propagation of the light and intensity of the light. So metallic nanostructures or plasmonic nanostructures in linear regime, they generate very exciting feature. So when two or more metallic nanoparticles are close to each other, they generate very high near field enhancement between them, in the gap between them, so-called hotspots, and these gaps, this field enhancement. And so in other words, we can confine the light in very, very sub-diffractive scales in these areas between the nanoparticles. These hotspots and near field enhancement, they are very sensitive to the change of the refractive index of the environment. That's why this sensitivity makes the plasmonics nanostructures very good candidates for sensing, because this sensitivity is so high. So by a little bit change of the refractive index of the around the nanoparticle, we can detect those changes and then interpret the existence, absence, or change in the characteristics of the materials around those nanostructures or sensors in this case. So in order to give you some idea that how sensitive they are, so it is an example of one of these studies I was involved many years ago when I was postdoc at Imperial College. And as you can see, these molecules, which are 2 to 7 nanometer alkyl molecules, they excuse me, they can be detected by plasmonic nanostructure. They are really, really small. 2 to 7 nanometer is nothing. They are very small, but as you see, they still induce some shifts in the position of the resonances, and that's why by detecting and interpreting those shifts, we are able to detect and even distinguish different kind of these molecules. And even more, not 2 to 7 nanometer, even if you go to sub-nanometer scales or single layer scale, so still metallic nanoparticles or plasmonics can be used for sensing. So it is another paper which I was again involved in those years. And here we showed that by the right design, we can even detect the existence of one single layer of graphene, which is around 3 to 4 angstrom in terms of thickness. But still, this near field enhancement are strong enough and are sensitive enough so that we can use them to detect such a thin layer of material next to our nanostructures. And but the issue is that when we go to the gas sensing, so the story is different, because these nanoparticles can detect some solid or in the liquid phase, they really work well. They change solid materials or liquid materials when they change the refractive index around the nanostructures. But when we are speaking about the gas existence, so the change they make in the refractive index are really, really low. As you see, for example, one example I have put here, the change in the refractive index between air and ethanol is 10 to the minus 4, which is really little, and it's hard to use metallic nanoparticles or plasmonics for gas sensing. Of course, some nice strategies have been proposed by the group of Harald Gissen many years ago. Actually, it was 2011. Yeah. So they used, again, they used this near field enhancement, but they used this palladium material that can absorb hydrogen gases. So they put it right in the area of the near field enhancement or hot spot of this triangle gold nanoparticles. And by shining the light and then exciting this palladium, they can absorb the hydrogen, and then they change the overall optical properties of the cell or of these nanostructures. As a whole, it changed, and by detecting those changes, you can detect the hydrogen gas around them. So the issue of this strategy was that these palladium materials, they get saturated at some point when a lot of hydrogen are already embedded there. So you need to heat them up then to regenerate the sensor. So plasmonics nanostructures for gas sensing, they have been still a big question and a big study, big direction of research. And we also were working on that, and it is the way we proposed to use these nanostructures. We proposed a few years ago when I was at Australian National University with colleagues and in particular the group of my friend Antonio Tricoli. So we proposed to have the ultra porous films or clusters on the top of the metallic nanostructures so that we could enhance the sensing volume of the entire device. And it was a very successful strategy over here. I'm not going into much detail, so if you are interested, you are very welcome to go and read this paper. But very, very briefly, so what we did, we had this ultra porous titanium oxide nanoparticles on the top of nanostructures. So here, first we studied the effect of different thickness of these porous films. And as you see over here, for people who are doing sensing by plasmonics, they would appreciate that, you know, even 3 micrometer of this ultra porous film, I think 98% porosity was the porosity of the films. It doesn't really change the position of the resonance, as you see here. Remember, a few slides ago, I already mentioned that even one layer of graphene can change, but here you see that the change which the 3 micrometer of this ultra porous film makes on the top of the metallic nanostructures, it doesn't really make a huge changes. So, but the good thing about this ultra porous film that increase the sensing volume so that we can detect on the order of 10 to the minus 7 variation of the refractive index by this strategy. Here, as you see in the results here, when we have only plasmonic nanostructures in this graph, so when we purge 4% of ethanol. So the change in the plasmonic resonance is not remarkable. But when you have this 1.8 micrometer, which is again in this paper, in the paper is already explained that this one is the optimum thickness, it's the best thickness. So in this thickness we get very remarkable change in the plasmonic resonance. And as you see over here, so it's very repeatable. And when you purge the ethanol, so you shift, when it's stopped, it goes back to the same resonance. And again, you can repeat it. And it's very durable, this kind of sensing. So we used it for detecting different kind of gases in air, acetone, toluene, ethanol, and as you see, they have different signatures, which was very interesting because if you get temperature into account here, and then by having this data set of different gases, so you will be able to use the same sensor not only to detect certain gases like acetone, toluene, and I don't know, ethanol, and say what is the gas. You can even detect the concentration of those gases if you have this data set. So it is very exciting and very interesting results. So which was very well received in the optical sensing community, and that's why we were very excited to continue in this research direction. And what we did next, we made it in a 3D fashion, because previously we had only plasmonic nanostructures on the bottom and this porous film on the top, and we had those nice results. So in this case, we went to 3D, we went to the 3D fashion here, and the plasmonic nanostructures or gold nanoparticles are distributed in the 3D way. And as you see over here, it really enables us to detect 0.01% of gases, and as again, just we did for toluene, ethanol, and acetone, and you see that there are still different signature for each of these gases, and indeed by this strategy we managed to detect 10⁻⁸. One more application of plasmonic nanostructures is that you can use the optical force generated by those plasmonic nanostructure. It is another piece of a study we have recently done with my collaborators mostly in Japan, Yoshito, my great friend, and the University of Tokyo. So as you can see over here, by having some asymmetric nanostructures, you can generate some side scattering. So the scattering will be in one side and the optical force will be generated in the other side. So in this case, by having this design, so you can have different kind of movement, you can have rotary movement or maybe just linear movement here. If I can show this video here, you by just turning on the light without moving the light source, just turning on and off, you can just turn on this rotary movement, or even just this linear movement over here, as you see, by turning on and off the light. So I want to emphasize here that on this study, these structures are driven by an incident plane wave with zero linear and angular momentum, because previously it has been shown that by employing the angular momentum or linear momentum of light, which I'll speak a little later, so we can move some particles, we can make some optical forces. But here we are moving these particles with plane wave, without any steering, without any oblique incidence, and just by turning on and off the light. And the main strategy here is to have a nice design to generate this asymmetric scattering by this asymmetric nano antenna of the plasmonics. So one more very exciting research area which we are doing at the moment at Advanced Optics and Photonics Lab in the UK. So we are combining these two directions. So we are using the optical force to trap some cells some very small and tiny sub-10 nanometer complex molecules, and then study them in their natural environment. So this research is ongoing. Unfortunately, I cannot say much more about it, but I want to emphasize that it is really interesting because you study these different substances when they are still alive and when they are still in their own environment. Because in other cases, when you want, for example, study some of these complex cells, you have to take them out from their environment and look at the optical and the electron microscope or other ways that in all of those different ways of the studying these molecules, you kill them and then study. So you cannot study them in a dynamic way. So in their natural environment. By this technique, by trapping them with optical forces and studying their optical properties, so you can really have a groundbreaking study on different kind of molecules which have not been possible before. So now I will go to the nonlinear regime, and I'm still speaking about the metallic nanostructures, and I want to share with you some of my experience, some results we got in nonlinear regime with these plasmonic nanostructures. When we are speaking about nonlinear regime, it means that we are going beyond this area. So it means that the intensity of the light after passing through the material or our metasurfaces actually doesn't depend linearly on the intensity of the incident light anymore. So here, the main feature is that the frequency of the light changes, which in the linear regime it didn't happen, but here it happens, and it has a lot of application. So based on the number and energy of this input and output, photons and light going to the structure, so we have very different nonlinear interactions in scattering, in emission, third harmonic, second harmonic, some frequency generation, and so on. And they have a lot of application actually in our daily life, but mostly at micro scale. So today, right now, nonlinear optics at the macro scale, not at nano scale, it's very influencing our daily life. So in different ways, in the spectroscopy, in the microscopy, or even in the optical fibers, it's something that we are using it every day around us in our daily life. But when we go to the nano scale, the story is very different, and we are not yet using nonlinear optics at nano scale. Simply because we still haven't managed to get high efficiency or usable efficiency that can be used without needs for enhancing or improvement in our daily life. So the reason is that in the micro scale, when you use different kind of nonlinear crystals, you can accumulate very weak nonlinear signals by having a lot of these unit cells next to each other, which they accumulate within the crystal. So based on the phase matching and the separation between them, so you can make sure that you enhance the nonlinear signal at the end of the day before you're using. But when you come to the nano scale, you don't have this phase matching and you don't have this structuring anymore. So it means that the intensity you receive drops, and you don't really have this chance to use it for real applications. So what happens? So people are trying to see how they can enhance the nonlinear signals at nanoscale by different kind of nanostructures. And obviously, Plasmonics nanostructures or metallic nanostructures have been one of the first candidates for this direction. So this paper is not my paper. This paper is published in 2012, and still maybe many years from the first paper of the Plasmonic nonlinear photonics. There are several papers before this, but the reason I chose this paper, because this one actually the paper which inspired me to nonlinear nanophotonics and plasmonic nanophotonics, because this paper very clearly shows that at nanoscale, you have more degree of freedom as compared to the micro scale. As you can see over here, for different type of dimers, when the dimers are disks or ellipse or rods, you have different, of course, nonlinear signal third harmonic generation. But for the rods, we have the highest one, which is something that you don't see at micro scale, because at micro scale, the more material we have, the higher signal intensity and higher efficiency you have. But when you come to nano scale, the material alone is not the main player. So there are so many other factors and so many other degrees of freedom, and one of them in the plasmonics is this near field enhancement and these hot spots. And as you see there, this plasmonic resonances, they can really enhance the nonlinear signal, which wouldn't be possible at macro scale because we don't have this phenomenon at macro scale. So in the last decade, and still there are a lot of papers and there are a lot of study to study the nonlinear signal by plasmonic nanostructures. We have been also very active in this area from the time when I was at Imperial College of Postdoc. So here, as you see here, by some complex structures and with some generating different modes and various modes, you can enhance the nonlinear signals, or even by making some by breaking some symmetry and having different symmetries here. As you see in the second harmonic generation, in this symmetry is much weaker, much stronger than second harmonic generation in this symmetry. And even taking advantage of this hotspot by putting some extra material in those hotspots here. As you see here in this nice study, we had the dimer, and obviously we had this hotspot in the gap of the dimer, and we put one small nanoparticle of ITO over there, and we managed to significantly enhance the nonlinear signal in those years. But at the end of the day, so the intensity of the plasmonic nanostructure didn't go to the level that can be used for application, and I will tell the reason in a minute. So that's why this issue and other issue made people think that probably they have to migrate to some other material. So despite very nice properties of metals, and in particular plasmonics, including a strong hotspot and durability, I have to emphasize on this durability, because the good thing about the plasmonic nanostructures is that they can be used for many years. I still can use the plasmonic nanostructures which I made in the beginning of my PhD in 2009. They still work perfectly fine. They do not oxidize, in particular gold. Of course, it is not the case for silver, but the gold, they do not oxidize, nothing happens to them, so you can use them for years and years. And it is a very good example of this piece of gold, which is for around 700 years ago, 7,000 years ago, but still it's there. It's called Mystery of Varna gold, and it is because of the gold properties that doesn't get oxidized. So you can use your devices for many years if it's not physically damaged. But still, despite of this nice advantage, there are some disadvantages. Plasmonic nanostructures suffer from ohmic losses. They absorb light a lot, and they have very low heat resistance, as you see over here, in particular for the nonlinear regime. When you are exciting some laser, when you are just putting some high power laser, when you want to excite the nonlinear interaction, you easily can burn. As you see here, it was a dimer, but it's already burned. And more difficulties in directionality, more difficulties in controlling the direct emission directionality of the light. So it's another problem of the plasmonic nanostructure. So I believe that Harald Gissen, who is one of the pioneers in plasmonics nanostructures and plasmonics in general, is going to give a talk in a couple of weeks, if I'm not wrong. Sometimes, yeah, in 20 days. I don't know exactly what he's going to speak. He's going to speak about topological plasmonics, but since he's pioneering plasmonics, I believe he will speak much more about the different aspects of plasmonics and the good application of the plasmonics in different areas. So because of those issues, mostly loss issue and low heat resistance, so people migrated to dielectric metasurfaces. Dielectric metasurfaces are based on the dielectric and semiconductor, or in general, high refractive index nanoparticles. So the good thing about them that they can have the field inside the nanoparticles, unlike the plasmonic nanostructures. So therefore, you get the magnetic field also involved and generated by this dielectric nanoparticles. So in addition to electric field, you will have magnetic field, and in addition to the dipoles, you can go to high order mode. So the dielectric nanostructures are capable to generate a zoo of resonances, unlike the plasmonic resonances, which was one, or maybe just with some tricks you could have several high order modes. But naturally, dielectric metasurfaces, they can generate a lot of different resonances, and each of them, they have different characteristics in terms of emissions, in terms of the intensity, and so on and so on. So they give us much more tools for manipulating the light matter interaction and light behavior. So a couple of weeks ago, Yuri in the same platform has given a talk on mirror resonance, nanophotonics, and metasurfaces. And if you are interested in more physics about this dielectric metasurfaces and application of them in different areas, I encourage you to watch this video. I believe this video is already available. The video of his seminar is available in the same platform. The same story with dielectric metasurfaces regarding the linear and nonlinear regime. So we can't categorize them in linear and nonlinear. And now by going through the applications, you can see that interestingly, they can offer very similar applications. So it makes us really, it makes our life very hard to answer this question, which one is the best. Of course, they are good for different applications. Let me speak about it, and then we come back to this question again. So for the linear regime, just a second, please. For the linear regime also, we can have this nanoparticles next to each other, and we can also generate some hotspot and near fields. But the point is that in the dielectrics, the intensity of those near fields are much weaker than the plasmonics nanostructures. But the advantage is that because they don't absorb light, this dielectric or silicon nanostructures, they do not generate heat. Here, actually, it was a nice paper. It's my friend Pablo Albella. Many years ago, he showed this effect very nicely theoretically, that as compared to the plasmonic nanostructures, which generate heat together with the hotspots, the dielectric nanostructures and dielectric hotspot, they are heatless and heat-free. And as you see here in this experimental result, we already showed it in 2015, that it is indeed the case. And silicon dimers do not generate heat, but plasmonics dimers and gold dimers, they can generate up to 80 degrees. So just imagine that if you have some sensitive material, sensitive cells or molecules or DNA or something on the top of your plasmonic nanostructures, so this heat can damage them. So that's why it is a problem for using those plasmonic nanostructures for sensing. Also, plasmonics can give much more sensitivity, but this heating is something for us to consider when we are thinking of the sensor. That's why sensing application with dielectric nanostructures became again hot. I write again because first the sensing by plasmonics was very hot area, then sensing by dielectrics was very hot area. But I want to emphasize that here, as you see, we are not really using much hotspots. We are not using a much very close nanoparticles, because anyway the dielectric, they do not generate very strong hotspots, but because of this lack of heating and because of this good sensitivity, you can use it for larger cells, you can use it for oil sensing, or as you see in this nice paper published by the group of Altuk in collaboration with Yuri and Dragomir. So, and of course, Andreas Tittel, my great friend, who drove this research study. So you can make some barcode pixel devices. So here the mechanism is that you have very sharp resonances at near infrared, and by matching and overlapping it with the absorption signature of different substances and different cells and molecules, you can use it for very nice sensing, and you can use it for a good sensor. Another application of dielectric nanoparticles in a linear regime is optical force again. So you remember I showed you some of the results with the plasmonic nanostructures, that we can make the this optical force, we can make this movement, angular movement, linear movement. But in this nice paper by group of Mikhail Kahl last year, they showed that you can do that with the dielectric metasurfaces too, but with some differences. You remember when I was speaking about the movement with the plasmonics nanostructures, which I showed done by Yoshito, my friend. So I emphasize that by turning on and off the light, and by using just plane wave, not oblique incident, just the normal incident over there, we managed to move those plasmonics devices. But here, because you are using the angular momentum and you are using the linear momentum and using waveguide mode to control the light momentum, you have to change the incident of the light. You have to use the oblique incidence, and you have to steer the light to move these nanoparticles. So this is very exciting, but it is different. The application, the same movement of nanoparticles, but this is different. So it is really dependent on what you need and how you want to use it. So it is not a black and white answer that, okay, optical forces in dielectrics or in metallics, which one is better? It's really dependent on your application here. But one interesting thing about this dielectrics, and in general, it can be also done by metallics, is tunable metasurfaces. Here is something that I really like, because in the regular optics like lenses, mirrors, they usually one element can have one function, one mirror, one lens, one prism. But when you go to nanoscale, you can have one device that can have several functions, so which is very exciting. So it can be used for plasmonics and dielectrics. Before I go to the dielectric, I said that in general case, for example, here you can fabricate your structures on some flexible substrate like PDMS by stretching them. You, of course, to change the separation between them, and then you will have different optical properties, or you can use the liquid crystals on the top of your metasurfaces. Here in this nice paper, it can be the dielectric nanoparticle. This paper is done by the group of Dragomir Neshev and Isabel in Jena, another friend of mine. So this here, this dielectric, and Andrei Komal, of course, the first author. This the metasurface, dielectric metasurfaces are at the bottom, and you have the liquid crystals on the top, and by applying the voltage, changing the direction of the liquid crystal, you can, of course, change the optical properties of the entire device, and phase change material that you can go from amorphous to crystalline phase. So there are also another interesting direction of the tunable metasurfaces. But one thing that it can be done only by dielectric metasurfaces, one tuning way, is that employing thermo-optical effect of silicon. Silicon has very large thermo-optical effect. It means that when you change the temperature of the silicon, the refractive index of silicon change. Some other materials like germanium and some other material also have it, but silicon has a very large one. And here in this paper, we a few years ago, first we took a thin film of silicon here, and you see these Fabry-Perot modes, and then just by heating it, you can see this shift, nice shift of the Fabry-Perot modes, showing that the refractive index is changing. Then we took this phenomena and this understanding to use in metasurfaces, and we made some metasurfaces, and by targeting some wavelengths and some certain modes, which was which is published in this paper. I don't go into the detail, but I want to say that mention the application that here, as you see, by controlling the temperature of these metasurfaces and surfaces, you can control the refractive index of them, and then you can make your surface transmitting the light or reflecting the light at certain wavelengths. I just want to remind gently that at these wavelengths, the silicon doesn't absorb light, so it either transmit or reflect the light. So it means that if it's not transmitting, it's reflecting, and vice versa. So we used it a couple of years ago by hard effort of my PhD student at ANU in Australia, Khosrow. We made very nice yin-yang image composed of two different metasurfaces. Here, as you see, they are very similar, but they are slightly different in terms of dimension. That's why the wavelengths and the resonances are slightly different. So by looking at one wavelength and hitting the whole structure, you can generate an image, and you can control the contrast of the image only by controlling the temperature here. In this video, if I can show you here, by increasing the temperature, you see that these areas in the left-hand side, which are opaque, they become transmissive, and the other areas also opposite way. Then we are heating up the sample. Then we, after that, again, we cool down the sample, and you can see that it goes back to the first phase, and these samples can be used for ages. Nothing happens to that. It's very durable. And as you see, you can really and nicely control the contrast of this image in a very nice way. So the issue here we had, it was the time of heating, and the question all the time we received that how long it would take. It would take, because we were using the actual heaters, it would take around maybe to 10 minutes to heat it up and then cool it down to come back to the first phase. But all the time we were receiving this comment that the time is not good enough for real application. That's why Khosrow put a lot of effort and a lot of time to come up with some nice way to do the same, to use the same phenomena electrically. And it is a very, very nice research and nice result, which we have just obtained, and it is still under review. Here, what we have done, we have made this membrane silicon metasurfaces. So the reason is written in the paper, so you will see soon. It's just I'm just telling you the main message here. And by having an ITO on the top, and then connecting it to the electrodes, and then by applying the voltage, so you can heat up the ITO, which is the local heater on the top of the structure. So then you can by electrically heat up the entire device and your metasurface to get different different optical properties. Very important thing here is that it's how we apply this voltage. Okay, if you apply from 0 to 4 voltage, so it is here. It's how you get the metasurfaces get heated, so it takes up to 17-18 millisecond here. So here I will show you later. So it is really fast millisecond, but it still is longer than what we can see by our eyes, because our eye can see around 10 to 13 milliseconds. So what we need we need to shorter switching time, so that we could use it for real application like displays. And here it's the strategy we took. it is the first time we are taking this strategy in optics, because this spike, you see this spike or voltage bias is something that it's done in the electronics, but in the optical switch it has not been done yet. And here, by using this spike and very sharp increase in the voltage, we could significantly decrease the modulation time here. And you see, as you see over here, we managed to get 625 microsecond modulation time, which is amazing. I want again to emphasize that our eye can see 13 milliseconds, and by having 625 microsecond of this modulation time, we are much faster than what our eye can see, and it opens a lot of application for display and other applications that are at the moment suffering for optical switches. So this video can show us that how we can nicely control this metasurface, you know, that can transmit the light or reflect the light. Here you see that we are electrically, we are changing the frequency here. And as you see, I have a very nice control on the frequency here. What you are seeing at the moment is not noise. It's just very fast on and off, which our eyes cannot see. So it is very groundbreaking research by combining all of this different understanding, thermo-optical effect of silicon, using local heater, and having a solid state switch, because the other switch, like for example what we are using in our display, it's liquid crystal, it's thick, but our device is less than 500 nanometer in thickness, but it can give even better performance, and it is transparent thin. And okay, so this one I want to just show this video too, that we can make different pixel here and control those different pixel in a different fashion. So as you see here, this different pixels are controlled electrically. So by this local and flash heating, we can have different pixels working as optical switch, which is very, very interesting. So here, this paper is not published yet. We hope it gets published soon, and we can discuss more details probably in the following conferences on this groundbreaking research. And then I go in the last part of my talk, which is nonlinear regime for dielectric and metallic, for dielectric and semiconductor nanostructures. So as I mentioned, the main reason of using the dielectric in nonlinear regime is that plasmonics get molten by high laser intensity. So the choice, the plasmonics actually, it's bottlenecked. So we cannot increase the intensity of the laser. That's why people are trying to use different material and use different platform for nonlinear generation. So it has been very hot area in the last few years, and mostly nonlinear generation with 3-5 semiconductors, because it has been known for many years that 3-5 semiconductors, in particular gallium arsenide families, they have very high second order susceptibilities. That's why they are very good candidates for generating the nonlinear signal at nanoscale. So this was started with this nice paper, theory paper by the group of Costa. He's among audience, if I'm not wrong. And they started this field by this nice theory paper proposing that we can use gallium arsenide nanoparticles and aluminum gallium arsenide nanoparticles to enhance the nonlinear signal. So after that, despite the issue that we really could not grow the 3-5 semiconductor on glass or silicon, and it was a fundamental issue, several groups at the same time, they tried to solve this issue to generate gallium arsenide nanoparticles, the group of Joseph Leo and Egal Brenner. So they did it by using some sacrificial layer and oxidizing that sacrificial layer. As you see over here, for example, Joseph Leo group, they did aluminum arsenide, then oxidize it to aluminum oxide, or the group of Egal Brenner, they used aluminum gallium arsenide as the sacrificial layer, then they made it aluminum gallium oxide. So as the result, on the top, they had this isolated gallium arsenide or aluminum gallium arsenide nanoparticles, which could generate a nice nonlinear signals. And it was followed by several other efforts. The group of Stefan Meyer, they just used it and the gallium phosphate wafer and just etch it down, and they still showed that you can get a good results, although it's on the same substrate. And also the group of Grange, and they made this nano wires, and they cut it and they generated some gallium arsenide nanoparticles, which enable to get these high signals, high nonlinear signals. But all of these studies which I mentioned, so they are still on the opaque substrate on either gallium arsenide or thick gallium phosphate, that they are not transparent in the visible range. That's why you cannot have it in the both forward and backward. So although all of this research is very exciting and interesting, they were limited only to the reflection. So it was where we proposed a way to fabricate these gallium arsenide nanostructures on glass substrate, so that you could get signal from both sides, forward and backward, here in this paper. And in this nanofabrication technique, which I'm not explaining here, but if you are interested, you can go to see in this patent or in this paper. So we managed to have these 3-5 semiconductors on very thin glass substrate, then get both forward and backward second harmonic generation. So it was followed by several other successful approaches to generate this 3-5 semiconductor nanoparticles on glass, again by a group of Giuseppe Leo and also Yuri Kifshar. And then they generate them, and they could study the forward and backward. But another main issue in these 3-5 semiconductors was that they have zero normal incident because of the very complex second order susceptibility. As you see over here is the nonlinear emission. So it is the pump, it's the fundamental coming here, and you see in the normal we don't have anything. If you see from the front view, in the normal we have almost zero. And here are the backfocal planes. The theory, it shows that it's the inner circle shows that what we can get with microscope, but experimentally, and outer is the entire outer circle shows the entire nonlinear emission. So as you see over here, then this and in the normal incident we have really low signal, so and almost zero signal. So it becomes a problem because all the nonlinear generated nonlinear, they go to the side. So that's why there have been several efforts to solve this issue by using some grating around the nanostructures, or by using oblique incidence to have the nonlinear signal in the normal direction, so that we could solve this issue and we could use them. And there was another strategy proposed by us to use different crystalline orientation of 3-5 semiconductors to solve this issue, because most of those studies which I mentioned in the last few slides, they were using 100 crystalline orientation, and we showed that by using other crystalline orientation like 111 or 110, we really can control the nonlinear emission here. So I want to remind that in the linear regime, because it's just based on the refractive index of the nanoparticles, so you don't see much changes. You don't see any changes in the linear properties if you use different orientations here. For all different cases, the linear scattering is exactly like this, identical. But when you go to nonlinear regime, you see that this crystalline orientation, they significantly are different. For example, for 111, at the different polarization of the input light, you can get the nonlinear signal at different direction and closer to the normal. Here in this case, you see that the closer to normal, you can get some signal. So very interesting thing about the this 111 gallium arsenide nanoparticle is that the A second harmonic efficiency is polarization independent, but second harmonic radiation is polarization dependent. It means that when you change the polarization, the efficiency doesn't change, but only the emission change, which is very exciting. And for 110 is even more exciting, because only by changing the polarization of the input, so you can control the forward and backward, and you can switch the second harmonic generation from forward to backward scattering, which is very exciting. That can be done by 111. And as you see over here, you don't have that problem anymore in the normal. You can have very nice signal in the normal direction. So by using 110, you don't suffer from that zero emission at 0 degree or in the normal direction. And as you see over here, only by changing the polarization of input, you can control the proportion of forward and backward second harmonic generation, which was very interesting finding a couple of years ago. And finally, because we get very good efficiency 3.5 semiconductors, which was not possible with plasmonic nanostructures, because we were bottlenecked in terms of the efficiency, but with 3.5 semiconductors we got very good efficiencies. And then here we managed to show a very good application, which is nonlinear imaging by these nanoparticles here. This paper published last year. So we use some frequency generation here. It means that in addition to the omega-2, which is the near infrared light, we will have one pump, which is still in the near infrared, but it is just to enhance the low intensity of the near infrared light. And finally, we will get the signal in the visible range. So it means that by this nanoparticles and metasurfaces, and by the right design and using right pump, what you can do, you can have the very weak near infrared signal. You can get it converted to the visible range, and you can see the light in the visible range, which has a lot of application, which we are working on them at the moment. But very interestingly, we realized recently that, okay, with some nice design and other designs and some strategies, which we are still doing, and it's not published yet, we can use other material to that level, and we can get high efficiency by other materials like silicon to that level that we can use it for nonlinear imaging too. Here in this nice research direction, which we are doing in our lab, so we are showing nonlinear imaging via third harmonic generation, not some frequency generation. I want to just emphasize that in some frequency generation, we have some extra laser, but in third harmonic generation, just have the input and output. So it means that you have only two wavelengths. So it is very exciting to show that with silicon structures also, we can do nonlinear imaging. That's why we go back to the questions that what are the benefits of other materials in this nonlinear nanophotonics? That's why in addition to 3.5 semiconductors and silicon and germanium, people have put a lot of efforts on 2D materials. So we have also done some recent we have also published some recent study on 2D materials. I'm not going to go into the details. If you are interested, you can go and see in these papers. But very briefly, with this MOS2 TMDC materials, which have the highest shown refractive index, even higher than silicon. So this material, we also managed to get a very nice tunable unidirectional nonlinear emission. And with some theoretical studies, we have shown recently that by some hybrid TMDC and combining them with other kind of dielectric and plasmonics metasurfaces, we can get very interesting enhancement and improvement in nonlinear efficiency and also in emission. So which, if you are interested, you can go and take a look in these papers to see the strategies we have shown for hybrid TMDCs for nonlinearity. So far I spoke about all these different plasmonics, dielectrics in linear and nonlinear regime, but still I haven't answered that what is the best material, metallic metasurfaces or dielectric metasurfaces are the best. So before going to that conclusion, from my point of view, I just want to say a few words which are important, that how we design these metasurfaces, because as I showed you, so we can use metallic or dielectric for sensing, for optical forces, for a lot of other things, for imaging. So how we design them, how we decide which one is better for that particular application. So the common way so far, even during my career, has been that we usually take all the parameters, different parameters, which you can see here. The parameters can be material parameters, geometry parameters, coupling effect, and so on. We keep all of them constant, and we choose one or two by some simulation techniques and simulation methods to see what is the effect of changing one or two things at the same time, to see that whether we can get that optical properties which we want or not. For example, here in this paper, what we did, we got everything constant: the height of the nanoparticles, the separation of the nanoparticles, and so on. We just changed the diameters, and you see there have been significant and remarkable change in the optical properties. Then we took which one, the one which was actually interested for us for our application. Or even in this paper some years ago, so we kept everything. Sorry, here we just kept the diameter. We kept the separation constant and change the diameter of nanoparticle. Here we kept the dimension of the nanoparticle the same, only we studied the effect of separation. Again, you can see huge effect on the optical properties, and more recently we kept all the parameters constant. We only changed the crystalline orientation, and as you see in different publications, just changing the crystalline orientation, they have very huge effects on the optical properties of the metasurfaces. So the problem of this approach is that the productivity is really low and very, very time and cost consuming. So the way to get over this problem is to optimize and engineer all the parameters at the same time, which is what we are at the moment doing. And the solution is marrying machine learning and photonics. So the race is started, not only us, a lot of other groups in the world, they are using machine learning to design these different kind of metasurfaces for various applications. And here is also our paper published in 2020, among one of the first papers in this direction. So we showed that how by machine learning we can design different metasurfaces to get the nonlinear signal which we want. So here Leishu is the brain. In our group is the brain of this technique, and we are very happy that we have here Leishu to help us to do the machine learning for our designs. So what was the reason of saying that? The reason is that, as you saw, machine learning can tell us that what parameters, including what materials of metasurfaces are good for what application. That's why my expectation is that in a few years, for each and every application, including sensing, including optical force, and a lot of other application, quantum application, which I didn't mention. So machine learning will tell us which one is better: plasmonics, dielectric nanoparticles, or plasmonics nanoparticles or dielectric particles. It's this debate probably is going to its end in the following years, because it won't be debate between humans anymore. It will be a conclusion by machine that for which application, what metasurface is the best. So I hope to some extent I managed to share my experience and my conclusion on this direction with you. I have to acknowledge a lot of collaborators. So I'm sorry that some of them are here, some of them are not here. And also during the papers which I showed, I'm really sorry that some of the papers have been missed. I'm pretty sure that I have missed some papers, so I apologize for that. So I want to thank all the collaborators who are listed here and who are not listed here. Very significantly, they help to do all of this very exciting research in different directions. And most importantly, I would like to thank my group here. At the moment, we are a small group, but we are growing. We are getting more students and more postdocs and more academics. As you see, our group consists of academics, not necessarily postdocs and one person. It's a large academic group, and every single of these people you see here, they are really genius in what they are doing, and I am the happiest guy in the world having this opportunity and this advantage to work with them. So they are actually the main force and the main power to do the research, and my job is trying to make sure that they are fed well. My job is to make sure that they eat good food to generate good research, and I hope that I'm good at it. So you can ask them if I'm good or not. So if you are interested in any of this research, or if you are interested in trying different food and different cuisines, you are very welcome to come and visit us in Nottingham, and we are very open to new collaborations. Last but not least, I want to advertise Optoelectronic Advances, the journal in which I am an associate editor. So our latest impact factor has been 9.6, which is pretty high. So it is a new and very dynamic and exciting journal. So if you have good papers, probably you better not consider our journal. But if you have exceptional and very good papers, then please consider our journal and submit it to Optoelectronic Advances, and we will be happy to review it for you. So thank you so much for the time. Sorry, I went 10 minutes beyond the time which I was given. I hope you are not bored, and I'm happy to get your questions.
Thank you very much for the very nice talk. And as said, we have time for questions. So people, either you just ask your question directly, you have to unmute yourself because you have been muted automatically. Or if you don't have a microphone, you can eventually write it in the chat and I will read it for you. So questions.
Dear Bogdan, I cannot stop sharing. Can you please stop sharing? For some reason, I don't know why I cannot find it. Can you guys stop sharing so that I can see the people who are asking questions?
You should have. Unfortunately, I cannot stop it, but maybe.
So because I changed this settings so that I could see only my slides. So I do not see this. Okay, let me try.
There should be you should see a red button probably on the top of your screen. And you just
I already removed that panel because it was disturbing me. I removed that panel. I cannot bring it back. Let me see. I'm trying. Okay. If you have any question, I'm happy to answer, but at the same time, I'm trying to